It is our second part of design of FIR filters. In first part of the lecture, we have studied different types of filters. What is the difference between FIR and IR filter? And we described some mathematical equations and steps in the design of ideal low pass FIR filter by using Fourier series expansion method. So let us solve one example to understand the complete design of FIR filter. Equation is given. Equation of frequency response, desired frequency response ht of e raised to j omega is equal to 1 or minus pi by 2 to plus pi by 2. What is mean by this? Let us plot ht of e raised to j omega versus omega. So here one axis is j omega, so one axis is omega and the other is hd of e raised to j omega, and it is 1. This is 1 up to it is minus pi by 2. Left side of this is minus pi by 2 and omega is plus pi by 2. So minus pi by 2 to plus pi by 2, that is the meaning of this. So it is the value of omega and this is 1. During these frequencies, it is a range of frequencies. What is the complete range of frequencies? It is minus pi by 2 to plus pi by 2. Okay, we never consider this minus in case of this frequency axis. So it is pi by 2 plus pi by 2. So it is pi. It means the frequencies we have 0 to pi radians. And degrees, these frequencies will be 0 degree to 180 degree. At the end of the example, we'll obtain the values of magnitude of frequency response, and we have the values of omega for 0 to 180 degree. So we are going to plot the magnitude h of z. Okay, it's a transfer function, and we'll get h of z values of desired frequency response, and we are going to find the magnitude in decibels, and we are going to plot magnitude in decibels versus omega in degrees. So that will be the complete design of low pass filter using Fourier series expansion method. So we have frequencies range, and this method is Fourier series expansion method. We have hd of n. This is the desired impulse response. And we have 1 by 2 pi integration of hd of e raised to j omega into e raised to j omega n, or minus pi by 2 to plus pi by 2. That is the range of frequencies for which we have to find the impulse response of the filter. We have hd of e raised to j omega, so this term equal to 1. So substituting this, we'll get this term. And if we integrate this, we'll get e raised to j omega n by using e raised to integration of e raised to x dx is equal to e raised to x. Integration of e raised to 2x dx is e raised to 2x divided by 2 is the coefficient. By using this, we have found the integration of e raised to j omega n is e raised to j omega n divided by jn. Okay, with respect to omega, we have integrated this. Substitute limit in place of omega, we are substituting this upper limit and lower limit. So we'll get e raised to j pi by 2n minus e raised to minus j pi by 2n or jn. Now use this relation of mathematics. E raised to j theta minus e raised to minus j theta divided by 2j. So this is equal to sine theta. By using this relation, okay, we are simplifying this. 1 divided by pi n e raised to j pi n by 2 minus e raised to minus j pi n by 2 divided by 2j. So this equal to sine n pi by 2. Here it is theta and here it's value of theta. So it is pi n by 2 is theta. This will become sine theta. Okay, here it's sine theta. So this will become sine n pi by 2 by 2 divided by pi n. Okay, already we have pi n here. So this equation, so we have obtained this hd of n, sine n pi by 2 divided by pi n. So this is the speciality of this, or this is the point worth remembering. So this impulse response is or minus infinity to plus infinity. Okay, and this is not realizable. Okay, we want some part of this. We have to truncate it for n equal to 11 samples. See, we have n equal to 11. It's a given in the example that order of the filter is n equal to 11. We have to design low pass filter, low pass FIR filter for this n is equal to 11. Therefore, so we have listed the steps in designing of FIR filter by Fourier series expansion method. Let us truncate this and we call this hd of n as h of n. This stands for desired frequency response. For simplicity, we are calling h of n now. Now it is sine n pi by 2 divided by n pi. We have this. Now we have to truncate this for plus minus n. Okay, we are writing n. So it is plus minus n is less than n minus 1 by 2. So what is n? N is 11 minus 1 divided by 2. So it will be 10 divided by 2. It is 5. So what is the range? So mod of n should be plus minus. It is so mod of n plus minus less than 5. Okay. So we have this h of n now. So let us obtain the values of h of n for different values of n. Okay. But we have to find what will happen if I substitute n equal to 0 here. So n equal to 0 and n equal to 0. So something over 0 is infinity. If I substitute n equal to 0, this h of n will be equal to infinity. Okay. So this is not value. Therefore, we are finding the value of h of 0 by putting n equal to 0 in our equation of hd of n. We have 1 divided by 2 pi integration of hd of e raised to j omega into e raised to j omega d omega. So in this, so here we have n. So put n equal to 0, we'll get the value of h of 0. So this is the value of h of 0. So we have this frequency response is equal to 1, and here we are putting n equal to 0. What we get? E raised to 0 is 1. With respect to omega, therefore we'll get omega. So 1 divided by 2 pi, integration of this term, simply integration of 1 with respect to d omega is omega, and its upper limit and lower limit. So when we substitute these values, we'll get h of 0 equal to half, which is equal to 0.5. So we have obtained the value of h of 0. Okay. H of 0 we have obtained 0.5. Now let us find the rest of the values. For n equal to 1, h of 1 equal to h of minus 1. What we are doing? So h of n is equal to h of minus 1. So this impulse response equal to the negative counterpart. N is the index right side and left side. So it is right side of h of 1 equal to left side h of minus 1. Therefore, by putting the values of n, sine n pi by 2 divided by n pi, just simply change the value of n. Okay. So how much we have to take? We have to obtain total 11 impulse responses. Okay. Coefficients of impulse response. So h of n is the impulse response, and we have some values for this h of n. The first value will be 1 over pi is 0.318. N equal to 2, which is equal to h of minus 2. So here we are putting n equal to 2. So I have calculated this and we'll get 0 divided by 2 pi is 0. N equal to 3. So it is h of 3 equal to h of minus 3, and sine n pi by 2 divided by n pi is equal to minus 1 by 3 pi is equal to this one. For n equal to 4, we'll obtain 0 because sine, so it is 4 pi by 2 will become sine 2 pi. We know sine 2 pi is 0. So no need to find sine 2 pi is 0. N equal to 5, h of 5 equal to h of minus 5. So we get 1 over 5 pi. So it is 0.0633. So let us substitute these values in transfer function. First of all, we'll define transfer function. Transfer function is defined using Z transform. Okay, so we have transfer function. So transfer function is generally, it is output divided by input. Okay, the h of z is the transfer function, and its equation is h of 0 plus sum of h of n z raised to plus n plus z raised to minus n. Okay, or n equal to n minus 1 by 2. So this is equal to h of 0 plus sum or n equal to 1 to n minus 1 by 2 is 5. n1 minus 1 divided by 2 is 5. So it is h of n into z raised to plus n plus z raised to minus n. Okay. Now elaborate this equation. Let us remove this summation symbol, and for n equal to 1 to 5, let us elaborate this equation. Why we are not taking n equal to 0 here? Because already we have calculated the value of h of 0 by putting n equal to 0. We have separate value of h of 0. Therefore, the summation begins with 1 to n minus 1 by 2. H of z can be obtained by elaborating this equation h of 0. Okay. Now simply multiply h of n with z raised to plus n, h of n z raised to minus n. So very simple expansion of the equation. Multiplication of terms h of 1 z raised to 1 z raised to minus n plus h of 2 z raised to plus 2 z raised to minus 2. Okay. First we have substituted the values of n. So we are putting the values of n equal to 1, n equal to 2, n equal to 3, n equal to 4, and n is equal to 5. Then we have obtained these values. Okay, putting values of h of n in our equation. Now we have values for this. H of 0 we have, h of 1 we have, h of 2 we have, just we obtained the values. H of 3 we have, h of 4 we have found, h of 5 we have. Okay, let us put the values of this. We'll get 0.5 plus 0.3183 into z raised to plus 1, z raised to minus 1. Okay, so it is 0. H of 2 is 0. The whole term becomes 0. So this term, this is equal to 0. And one more term is 0. H of 4 is 0. So this is equal to 0. So these two terms are 0. Okay. Now, this equation is not realizable. This impulse response, the transfer function is not realizable. Not realizable. Now what we have to do? We have to delete this impulse, this transfer function of the system by multiplying with z raised to minus 1, n minus 1 by 2. The amount of delay. So we are delaying here. So we have to transfer function of realizable filter. How to obtain the transfer function of realizable filter? By multiplying h of z by z raised to minus 1, n minus 1 by 2. Okay, what is z raised to minus n by 2? So it is z raised to minus 1 into 11 minus 1 divided by 2 So this will be equal to z raised to minus 1, 10 minus 1 divided by 2, which is equal to z raised to minus 5. Okay, and we got minus 5 here, z raised to minus 5. Now we have already h of z. This is the complete s of z. We have neglected 0 terms. Now what is the next step? Just multiplying h of z raised to this term, h of z raised to this term into this term, z raised to plus 1. Again, this term with the second term. Okay, this term, we are multiplying this term and we are multiplying this term. Okay, so we got the first term 0.5 z raised to minus 5, 0.318 z raised to minus 5, z raised to plus 1. Okay, and similarly we got these things. Now what we have to do? We have to use, next term is use a raised to a dot a raised to b. Okay, it is a raised to x. Let us take a raised to x into a raised to y. So it is a raised to x plus y. Base is set. Okay, so it is a raised to x plus y. By using this, we can simplify the next step. So it is z raised to minus 5, z raised to minus 5 into z raised to 1. So this becomes z raised to minus 5 plus 1. This is equal to z raised to minus 4. Okay, so this is z raised to minus 4. So simple calculation using this relation, we are simplifying this. Okay, now we have this transfer function and we are calling this as h of z. We had h of z. Now just we are obtaining the realizable transfer function in terms of z transform and we are calling it as a h dash of z. Now what are the missing terms in this? What are the missing terms? We have z raised to minus 5. We have 4, 6, minus 2, minus 8, 0 and minus 10 we have. Okay, what is missing is z raised to minus 1, z raised to minus 3, z raised to minus 7 and z raised to minus 9. These terms are missing. What we should do now? We have to take these terms, we take the coefficients of this as a 0 and we can write this as, let us write 11 coefficient. Okay, n is equal to 11. Now n equal to 11. Therefore, h of 0 equal to h of 10. Okay, so from where I am collecting this? H of 0. So this term, this coefficient. Okay, and this coefficient. So it is h, z raised to 0 means what? It is h of 0. Z raised to minus 10 means what? It is h of minus 10, h of 10. Okay, therefore h of 0, h of 10 equal to same value. So it is the same value. Both are having the same value. Just I am collecting from this equation. H of 2 equal to h of 8 equal to 0.16 from this equation. Okay, 0.16 and h of 8 0.16. Okay, 0.318. H of 8. Where is h of 8? H of 8 is here and h of 2. H of 2 is here. Okay, both are having negative value. So minus, actually it is minus 0.16. H of 3 and h of 7, they are absent, therefore it is taken as a 0. H of 4 equal to h of 6 equal to 0.3183. Whereas h of 6 is here. So it is h of 6 and h of 2. This one, h of 4. Okay, h of 4, h of 6 are same. We have the values of the impulse responses. Coefficients of z are h of n. Next, the frequency response in terms of Fourier series expansion. So we have completed obtaining the coefficients in terms of impulse response. Now we have to write the frequency response in terms of Fourier series expansion. In this method, so this equation represents the Fourier series, okay, which includes only cosine part of the Fourier series. So it is A0, so DC value, and this is associated with frequencies. So in this equation, we have different frequencies. Omega, range of omega is 0 degree to 180 degree. Where it is given? It is given in the example itself. It is given in the example. So it is minus pi by 2 plus pi by 2. So it is, while adding this, the minus sign won't be in consideration. Pi by 2 plus pi by 2 will be simply pi. So it's a 0 to pi, radians means 0 to 180 degree. Now before that, we have to obtain the coefficients an. So these are the coefficients we have to obtain using a special formula for that. So the value of an is calculated by using this formula. Okay, so an is equal to 2 into h of n minus 1 by 2. So here it is 2 into h of n minus 1 by 2 minus 1 minus n. What will happen in this case? Simply the value of n will change. N equal to 1, it is 2, h of n minus 1 by 2 minus 1. So it becomes L1 minus 1 by 2 is 5. So 5 minus 1, 2h of 5 minus 1. So 2, 5 minus 1 is 2h of 4. 2h of 4. What is the value of h of 4? We have in the previous equation. Value of h of 4 is here. This is the value of h of 4. Okay. Substitute value of h of 4 on this equation. So it is h of 4. The final value of h of 1 will be this one. Okay. Similarly, we can obtain the value of a2. a2 is 0. a3 is minus 0.212. And when you substitute n equal to 4 in this equation, so we get it's a 0. And n equal to 5 in this n equal to 5 will get h2 into h of 0, that is 0.127. Now, how to find the value of a0? By using this formula. Use this relation. A0 is special formula, an is a different formula. So a0 equal to h of n minus 1 over 2. We'll get h of 5. So value of a0 is 0.5. Where we have to take these values? We have to take these values into this equation. Equation number A. In equation number A. This equation will expanding this equation as a0. Now summation a0 plus sum over n equal to 1 to 5. This is our summation limit. An cos of n omega. Okay. So if you put n equal to 1, it will become a1 cos of 1 omega. If you substitute n equal to 2, it will become a2 cos of 2 omega. If you substitute n equal to 3, it will become a3 cos of 3 omega. Okay. In between this, there is a plus sign because it is a summation. N equal to 4, a4 cos of 4 omega. N equal to 5, a5 cos of 5 omega. Okay. What's happening here? The frequency is increasing. The frequency field is increasing. And what will be the response of the filter to increasing frequency? Okay. That is our test. We have to test the system, FIR system, in ideal low pass case, whether it is allowing low frequencies and blocking or stopping the high frequencies. That is the check. That is design of the FIR filter by using Fourier series expansion method. Now, substitute this 0.5, substitute these coefficients a1, a2. We have obtained this a3, we have obtained a4, we have obtained a5. Okay, so this is 0.6366 minus 0.213 minus 0.127. Okay, now what is the next step? Next and final step. We have to change the value of omega. We have to change the value of omega. For each omega, okay, omega is the frequency, cosinusoidal part having omega. And this omega will change. Okay, in first case, omega equal to 0. First case, omega equal to 0. Okay, omega equal to 0. So we'll get one value. For second case, when we change the case, n equal to 10 degree. So omega will be 10 degree. So omega will be 10 degree. And here omega will be 10 degree. For third case, omega will be 20 degree. Omega will be 20 degree. Omega will be 20 degree. In this way, we can obtain the value of h bar of e raised to j omega. Okay, we have labeled this h bar of e raised to j omega. It is the frequency response, okay, which we are obtaining finally. We have labeled as h bar of e raised to j omega because it is a new equation. Now, find magnitude. Okay, so I have calculated for one value. We can calculate for all the values using calculator. So, this one, omega equal to 0, cos 0, cos 0, cos 0. It was cos 1 omega, cos 2 omega, or cos 4, pi omega. According to this equation, it is cos pi omega, cos 3 omega, cos omega. So this cos 0 is 1, cos of 0 is 1. So we got this value, 1.0516. Now we have to convert this value into decibels, because we have to plot the frequency response, which is in decibel, versus the frequencies. Okay, omega represent the frequencies, angular frequency. We are substituting in degrees. So we can obtain the value of h of e raised to j omega in decibels by using this formula. Okay, 20 log to the base 10, 1.0516. Okay, what is this? So this is nothing but h bar of e raised to j omega. Okay, it's magnitude. Final answer is called magnitude. Magnitude we are putting here, and we are obtaining 0.437 in decibels. Okay, repeat this for all values of omega. Okay, now what is the limit? Up to what value we have to substitute omega? It is given in the example design problem. What is our design problem? Our design problem is we have to plot the frequency response, which will allow frequencies or minus pi by 2 to plus pi by 2. Okay, and this is omega axis. And here we have h bar of final notation is h bar of e raised to j omega. Okay, this is the final notation we are using, and we have decibels here. Okay, we can write this to the right side also. Okay, this is this ideal case. So I have calculated the values of h bar of e raised to j omega magnitude in decibels for different values of omega, and this is the final table of that. So degrees, so 0 degree, you will get 0.4 here, 0.4 decibels. I have taken one digit. So 10, omega equal to 10, 0.21, omega equal to 20, minus 0.26. For 30, so minus 0.51. For 40, 0.21, 50, 0.42, 60, 0.7, 70 degree. So this is the in degrees, 50 degree, 40 degree, okay, and so on, 0 degree, 80 degrees, 90 degrees. And here for 80 degrees, it starts falling the gain. Magnitude response starts falling. It's not gain, it's a magnitude response. Magnitude of frequency response. So minus for 90 degree, there is a fall by 60 dB, minus 60 dB. Okay, so it's a fall in the gain. Minus indicates fall in gain. Sorry, fall in magnitude of the frequency response. It's not gain. So 110 degree, 130, 150, and so on. So minus 30, minus 26, minus 24 decibels of fall in the magnitude of frequency response. So to make it easy, so we have two axes. One is omega. We are representing in degrees. So it is pi by 2 is given condition. So, and its maximum limit is pi. So I have taken 0. So it is 0. Minus 10 indicates the fall in gain, fall in magnitude of frequency response. And above this 0, so it is plus 10. So here it is plus 10. So more than 0. Okay. So we have demarcation line. This line is demarcation. And on that, we have labeled 10 degree, 20 degree, 30 degree, 40 degree, 60, 70, and so on up to 120 degree. Now, if you plot this 0 degree, we are getting 0.4. So it is somewhat exaggerated, but it's close to 0. Okay, it is close to 0. And it's a 0.21. Again, it is above this axis. Green line indicates the 0 dB. Okay, and above this 0, it's a positive dB and it is negative dB below this. So it is minus 0.6. It is coming below this line. And this we are getting the different points for the different values of omega in degrees. So here the gain starts falling. Okay, gain starts fall in, sorry, it's not gain again, I'm saying gain. So it's a magnitude of frequency response starts falling here, fall in magnitude. Okay, what is the fall? It is called negative fall in magnitude response. So after that, after 90 degree, so we are getting the fall in the gain. So minus 6. So I have taken approximate minus 6 here. So it is from that it falls, and here it's right somewhat. So this is here in this case. So this band is called pass band of the filter. So this one is pass band of the filter. What is the pass band of the filter? So it is 0 to pi by 2. Okay, this is called pass band cutoff frequency. Below this, we have magnitude response. And above these frequencies, from this to this, 130. What is this? So this is the transition band. The gain is not falling suddenly to 0. Transition band. So there is a monotonous decrease from this value. Okay. So it is minus 90 degrees. So minus 6. So minus 6. Okay. And here up to 130. Okay. Or we can say it's 125 degree. Here we are getting this one. So this point is omega s, stop band frequency. Okay. So this is not ideal case. So it happens, there is a monotonic decrease in the fall in the magnitude response, and the filter is not allowing, should not allow these frequencies, but there is some transition, and between this transition, instead of sharp fall, there is a monotonous fall, and that fall is called as minus 60 dB fall in the magnitude of frequency response. Okay, and here it is allowing some magnitude, some values to the magnitude response. Therefore, this is called as stop band. Stop band. So what is the range of stop band? So omega s to pi. So this stop band is omega s to pi. Okay. And this variation, so this is called pass band ripple. This variation is called pass band ripple. It is denoted by 1 plus minus dou 1. Pass band ripple is denoted by 1 plus minus dou 1. Okay. And this is called stop band ripple. It is denoted by dou 2. Dou 2 is what? Dou 2 is stop band ripple. So this is the stop band ripple. So thus we have completed the design of ideal low pass FIR filter by using Fourier series expansion method, and we have completed all the steps, and finally we got the magnitude response of ideal low pass FIR filter.